Tutorial for homework number 22 on the first law of thermodynamics. For problem 1, we have to find the final temperature. If the heat energy put into the system is 7780 joules, if the mass of the water is 3 kilograms and the initial temperature T initial is 10 degrees centigrade. Alright, so we want to find the final temperature, and we know that the Q, or the heat we put into the system, is equal to the mass times the heat capacity of water when it's a liquid times the final minus the initial. So we know the mass, we know the heat capacity of water is 4180 joules per kilogram per degree centigrade. So we just have to rearrange this equation and we can find what the final temperature has to be in degrees centigrade. For problem 2, we're told that an automobile system holds a volume of 9 liters, so V is equal to 19 liters. And we are asked to find how much heat it absorbs for its temperature to rise from an initial point of 20 degrees centigrade to a final temperature of 91 degrees centigrade. Alright, so we're told it has water, so we use the same seawater from your textbook. And so the heat it absorbs is equal to the mass times the heat capacity times the change in temperature, so T final minus T initial. And since we're given the volume of water and we want to find the mass, we know that the density is equal to the mass divided by the volume. So the mass that we're trying to find for the water in this equation will be the density of water multiplied by the volume. So we have to find the density of water from our textbooks, plug it into this equation, and solve to get the mass of the water for this volume of 19 liters. Alright, so for problem number 3, we're told that we're asked to find the specific heat of a metal substance. So the specific heat C, if we have 144 kilojoules, so we have to convert that to joules, is needed to raise the mass of 5.7 kilograms from an initial temperature of 20 degrees centigrade to a final temperature of 30 degrees centigrade. Alright, so we can still use the same equation here. The heat we put in is equal to mc times T final minus T initial. And we can solve now, since we know the mass, we know Q, and we know the change in temperature, to find the heat capacity of this particular metal. So for problem 4, we're given a two-step process. So we have pressure on the vertical axis and the volume on the horizontal axis. And we're told that a system goes from some pressure initial position in phase space where the pressure is 2.2 atmospheres and its volume is 6.8 liters, to another point here where it has a volume of 10 liters and a pressure of 1.5 atmospheres. Alright, so as we learned in class today, the work that's done depends on the path you take. So in this program, we told that it goes first down from point A to point B. So it has a constant volume and it changes its pressure. And then it goes from point B to point C. Right. So, and we told that the temperature reaches its original value. So the temperature at this point here is equal to the temperature at this point here. So delta T is equal to 0. So since delta T is equal to 0, we know that we have an isothermal process going from A to B back to C. Alright, so to solve this problem, to find in part A the total work done going from here to here to here. So the work done going from A to B to C will be equal to the work done going from A to B plus the work done going from B to C. And we said that the work done is generally equal to the integral of the pressure and the change in the volume. So the work done going from A to C. So we're going to break this up into two parts. We're going to find AB and then BC and then sum them up together. All right, so going from A to B, the pressure goes from 2.2 to 1.5 atmospheres, but we see that the volume remains constant. So since volume is constant, this dV is 0. So the work done going from A to B is just going to be 0 joules. And so we cannot calculate the work done going from B to C where we have a change in volume. So the work done going from B to C will be equal to the integral going from B to C of the pressure dV. And going from B to C, we have the pressure being constant, but the volume changing. So in this integral, the pressure can come out here. So we just have to integrate. And we can use the pressure at point B. And we're going from dV, from volume B to volume C. So this is just equal to the pressure at point B multiplied by the volume at C minus the volume at B. So we can go up to the graph here. The volume at C is 10 liters, and the volume at B is 6.8 liters, and the pressure here is 1.5 atmospheres. So we just have to put that in this equation here to find the work done going from B to C. And we can plug these two values now back into this equation here. So we found that WAB is 0, and then WBC is the value we find here, which is PB times VC minus VA. VC minus VB. For the second part of the problem, we actually find the internal energy change in this process. So remember that the change in the internal energy is equal to 3/2 the total number of particles times K times delta T. So T final minus T initial. And we're told in the problem that the temperature reaches its original value. So the delta T here is 0. So change in internal energy will be equal to 0. And again, this is true because we have a process which is isothermal.